So yesterday I was talking about reaction force systems that are exerted by various kinds of supports. These supports are often attached to those rigid bodies which are of interest to us. We want to examine how a rigid body will move in space, and some of those may be having some supports. Our attempt here is to understand how we draw the reaction force system of a given type of support. These two supports I discussed yesterday also. One is the fixed support, the other is the ball and socket type of support. Let's review these once again and then we will look at some other types of supports. So for the fixed support, this is my body of interest, rigid body of interest, and I want to draw the free body diagram of this rigid body. Now this is only a part of the rigid body. There is more part of it on the top side. We are not shown. And there must be an applied force system acting on the RB, which again is not there originally in this figure, but let me put this something like maybe at point C, FR at point C, and then CR at point C. So this is applied force system. And in response to this applied force system, the support will generate what I call as the reaction force system. It reacts to the applied force system. My focus of attention is only the reaction force system. So when I am trying to draw the free body diagram of this body, you can call this as the truncated free body diagram. Truncated. Truncated means not complete, and it is truncated because the applied force system is not shown. That is not my concern right now. Okay. Now, since it is a fixed support, it will have or it can have non-zero force components in all three directions and non-zero torque components in all three directions. Those three directions are referring to this coordinate system, what I have shown here. This is my working coordinate system. With reference to that, I am saying three directions. So I will draw this reaction force system. I will put Fx, an unknown scalar, Fy, Fz. Okay. I will put Cx. This is the x component of the unknown torque at point B. I'll put Cy and I'll put Cz. 6 unknowns. If I want to put this reaction force system in vector form, it will be this. CRB, because it's at point B I am putting this unknown force, so the associated torque is called CRB, and that has these unknowns. Six scalar unknowns. Then you proceed ahead and try to see whether you can find these or not. That's a different step. I'm not going that far. My attempt is only to identify the unknown components of the reaction force system. Okay. The next figure on the right hand side of the slide, this is the body of interest. This is the support. This is the ball and socket type of support. If I have to draw the free body diagram or the truncated free body diagram of the body of interest, it will be like this. Again at point B, I will put Fx, Fy. Now x and y I am referring to the same directions what I had here. Different object, but I am not redrawing my working coordinate system. It's the same. Fz. 3 scalar unknowns. That's all. Fx, Fy, Fz. There is no need to draw Cx, Cy and Cz because the support is incapable of generating these. Ball and socket support cannot generate these reactions. This is the nature of the support. Another type of support shown on the left hand side, it's called bearing support. This is the support. This whole thing is the support. This is the support. What is the body of interest? Rigid body of interest. The body of interest is this. Again, it is truncated. This is the body of interest, the rod. Now the rod, and the bearing, they are interacting at multiple points, right? Must be a the interactive force must be a distributed force. I don't worry about that. I will just write the simple resultant, say at this point B. I'll draw the free body diagram of the rod. Coordinate system shown here. X is along the axis of the rod, Y is normal, Z is the third direction. What all should I draw here? Now before I can judge what all should I draw, we should know what all the support can offer. It is given that the support does not interfere with the free translation of the rod in the x direction. It means there cannot be any fx component. It is also given that if you try to move the rod along y direction, the bearing support will not allow it to translate in that way, and thus you must put an unknown force Fy coming from the bearing onto the rod. If you try to translate the rod along z direction, the bearing will not allow that, and that's Fz should also be put there. Two unknown force components this can offer this support. Now let's go to the torque components. The torque component will be judged whether a component will be 0 or not by asking this question: whether the bearing interferes, resists, tries to stop the free rotation of the rod along its own axis. Does the bearing offer any resistance to it? You ask the designer says no, he has designed it in such a way there will be no resistance offered by the bearing when the rod tries to rotate about its axis, and that is why Cx must be 0. You need not put that. Cx is 0. Fx was also 0 and Cx is also 0. Fx was 0 earlier because it's free to translate. Cx is 0 because it's free to rotate. Then I ask the question whether the bearing will allow the rod to be rotated with an angular velocity along EY direction. Can the rod freely rotate with an angular velocity along EY? No, it cannot. That's the way it has been designed, the bearing support. Thus, you should put Cy, an unknown, which needs to be found. Then you ask the question, will the bearing resist the rotation of the rod with angular velocity about z-axis? About z-axis. The designer says yes. It's almost clear from the figure also. And that's why you should also put a Cz here. So, 4 unknown scalars. Four unknown scalars in this case. We do draw sketches of various kinds of supports. But I want to tell you that if there is any confusion in your mind about what kind of resistive force and resistive torques the bearing can generate, you are free to ask the designer about it. What I'm trying to say, we try to draw figures as explanatory as it can be, but still, if you are solving the problem and it is not clear, it is your right to ask whoever has drawn this figure, whoever has designed the support. That information has to be given to you. So it is not a puzzle that looking at the figure you have to infer. This is not the exercise we are interested in doing. All right. Let's come to this support. So this is the object of interest. Body of interest is this rod. It's lying on a rough surface. It's touching a rough surface. All right. Touching a rough surface. And it's also given, it has a single point of contact. Single point of contact. Let's draw the free body diagram of this with the reaction force system. So will the surface resist if we try to move it in the x direction? This is x. This is y. This is z. Will the support, the rough surface, resist the motion of or the translation of this rod along x-axis? The answer is yes. Because it's a rough surface, there will be some friction force acting, and thus you must put Fx here. Along y, yes, it looks like if you try to lift it, if you try to translate this rigid body upwards, there will be no force coming from the ground. But that's only half the story. We don't know whether the rigid body has a tendency only to move upwards. It may have a tendency to move downwards also. And if it is trying to translate in the downward direction, indeed, the surface will generate reaction. And that's why you should include Fy. You should not ignore that. Now you may argue, why should I put Fy in upwards direction? I should put it downwards direction. You can put that, doesn't matter. You put it upwards or downwards, it's fine. You will get the value appropriately when you finally solve for the unknowns. But the point is, you should put an unknown there. That is important. You should not, that Fy should not be absent from your FBD. That is the important thing. Z direction, if you try to translate the body along Z direction, will the rough surface resist that? Yes, it will, because there is friction force. I put Fz. And again, I am not worrying about which direction I put Fz, along plus or minus. It should be non-zero. How about Cx? Should we put any Cx or not? Now here it is given that this object, there is a single point of contact. Single point of contact. Now see, for any torque to be generated, there has to be a couple of forces. Right? For any torque to be generated, there has to be a couple of forces. Couple of forces are two forces which are equal in magnitude, opposite in direction, and different lines of action. If the two objects, the body, the blue body and the rough surface, has just one single point of contact, there cannot exist a couple of forces between them. I repeat, if the blue body on the right hand side of my screen, the blue body and the rough surface have single point of interaction. There cannot exist an interactive couple. For a couple to exist, there must be at least 2 points of interaction. But here it is given there is single point of contact. So couple cannot exist. So when couple doesn't exist, torque cannot exist. And thus, in this case, you don't have to write. I know for sure that Cx, Cy and Cz are 0. Single point of contact implies no couple, no interactive couple can exist. Okay, and that is why I can confidently put Cx, Cy and Cz to be 0. So that's the free body diagram or the reaction force system. Only 3 unknown scalars in this case. Alright, let's move to some other kinds of support. Two-dimensional supports. Whatever I showed on the previous slides, I call them three-dimensional supports. Three-dimensional means the reaction force system can potentially have force components in 3 directions and torque components in 3 directions. And now I am talking about two-dimensional support. Two-dimensional supports will generate coplanar reaction force system. When do we use two-dimensional supports? When the applied force system is coplanar. Okay, and we know that the motion of RB is planar. What is planar motion? I have defined it 4-5 classes ago. When we know that the applied force system is coplanar and we know that the motion of the rigid body is planar, supports will also behave like, or the supports will offer coplanar reaction force systems. Coplanar reaction force system. So if this plane of motion or the plane in which the force system is being applied, it is in this plane. What I am saying is that the reaction force system can have Fx, it can have Fy, it can have these two components. Fz is trivial. We don't have to worry about that. And as far as torques are concerned, Cx is trivial, Cy is trivial. You don't have to draw them. Cz can exist, which we will show like that. So Ez is coming out of the plane. At max, you can have 3 scalars, 3 unknown scalars. At max, 3 unknown scalars will come on the FBD of the body of interest. Contrast this with a general 3-dimensional support that I was talking about earlier. At max earlier, it was 6 unknown scalars. Previous slides. Okay. Now with two-dimensional supports, coplanar reaction force system. At max, we will have three unknown scalars, Fx, Fy, Cz. That too will appear in some special supports. There may be sub-supports in which even less than three unknowns will be there. Let's have a look at them. Some more examples. Two D supports. And let's have a look at the figure on the right hand side first. That's simpler to understand. This is the body of interest. Rod or something attached to the rod. There is a pin here. And then you have this support. So this is called a pin support. It's written here. Pin or hinge. It's also called hinge support. Pin support or hinge support. Now this is a 2D support. It's behaving like a 2D support because the two conditions are being fulfilled. We know that all forces, applied force systems, are in the plane of the screen, and the body of interest, which is this, is having planar motion. And now I have to draw the reaction force system. What will that be? This is my body of interest. I have already said maximum, at max we can have Fx, Fy and Cz. This is my coordinate system. Should I put Fx here? How do I judge whether to put Fx or not? Remind yourself of the guideline that I mentioned yesterday. If we try to move the body, if we try to move this point B on the body towards in X direction, will the support allow or will it resist? Clearly it will resist. Pin joint will resist, and that's why I will put Fx. The next question I ask, if I try to move the rigid body, if I try to move the point B of the rigid body upwards or downwards, will the pin joint allow that or will it resist? It will resist, and that's why I will put Fy. So force components done. Coplanar force system, coplanar reaction force system, no need to think about Fz. Now go to the reaction torque. Cx and Cy do not matter. We only have to judge whether Cz should be put or not. So should Cz be put on this? How do I judge? I ask the question, if I try to rotate the rod with an angular velocity having component along Ez, will the support resist it? It seems the support will not resist it because it's a frictionless pin or hinge, and that is why you don't have to draw Cz. Cz is equal to 0. That's all. There are two unknown scalars in this reaction force system. Pin support. Only Fx and Fy are unknown. Now let's come to what I have on the left hand side. Actually, I have many types of supports here. And in engineering community, we call such supports by some names which describe their shape. First two are called, if you see a support like this, engineers will call that as a roller support. Another symbol for roller support. If you see something like this, it will be called a rocker support. And then this is a very simple case. You have a rod on a frictionless surface. Now all these four things have been grouped together because in all these four cases, the reaction force system will be similar. What will be that reaction force system? So this is my body of interest in all of them. The blue color rigid body in all these four figures is what I have drawn here. Blue color RB. I want to draw the truncated FBD of this. Now all these supports will try to resist the motion of the RB if you try to translate the body vertically in the vertical direction. They all are supposed to resist, and that is why I will put Fy. All these types of supports are designed so that they don't resist the motion of the RB in horizontal direction. This is a given information to me, and that is why there is no need to put Fx. Fx is 0. Further, you see that in the first three cases, this is a pin joint, this is a pin joint, this is a pin joint, and in this case, it is a single point. This is not written here, but this is a single contact, again, like last time. One point contact. One point contact. Since it's a one point contact, it cannot generate any torque. Cz will be 0. Because of that reason I am saying. For rocker and rollers, for the rocker support and the roller support also, since there are pin joint here and they are assumed to be frictionless unless specified otherwise, there cannot be any Cz. So this is true for all the four figures shown here. And thus, in all the four cases, the reaction force system will have only one unknown scalar, and that is Fy. Okay. Now, in the first three cases, rollers and rocker, even though it looks like, pay attention to this, even though it looks like the way the drawings have been made for the rollers and the rocker support, that if somebody tries to lift, at least for this and this, it looks like somebody is trying to lift, there will be no Fy. Looks like. But do not make your judgment in that way. These drawings are there to convey only this much, that Fy is non-zero and Fy can actually be less than 0 or greater than 0. Both are acceptable solutions for first three. For rollers and rocker. Okay. For frictionless surface, of course, Fy can only be directed upwards. In this case, Fy will be going upwards. The reaction will be upwards. But for the first three, don't be misled by the figure. Fy can be greater than 0, upwards or downwards. Okay. Possible. Couple of more examples of 2D supports. Let's go to the one on the right first. This is called a fixed support. I have shown you a fixed support earlier also, but that was a general three-dimensional fixed support. This is the 2D version of this fixed support. And if I have to draw a free body diagram, truncated free body diagram of the blue body here, body of interest, I will put Fx, I will put Fy, and I will put Cz also. Why I put Cz? Because the nature of this support is such that if you try to rotate the body of interest about an axis which is perpendicular to the plane, this support is not going to allow you. It means it is capable of generating Cz, and that is why Cz will come here. Three unknown scalars. Two more types of supports I have shown here on the left side of the figure. In this case, the free body diagram of the body of the FBD of the body of interest will be an unknown force in this direction. What is this direction? This is perpendicular to the slot. Here there is a pin here, and this has freedom to go in these two directions. It is frictionless. Since it is frictionless, I am not putting any force in this direction, putting a force in the normal direction, one component, and I am not putting any Cz because the support cannot resist the rotation of this blue body in this direction. It cannot. So Cz is 0. So here we have only one unknown scalar. The other support shown on this same figure is collar on frictionless rod. Collar on frictionless rod. Now since it is frictionless, the only force component will be normal to this rod on which it is sliding. There will be a force in this direction perpendicular to this. Okay, so this is the frictionless rod. Frictionless rod is here. There will be an unknown force in direction perpendicular to that. And again, there is a pin here, and that is why this support cannot offer any resistance to the motion of this free body or the rotation of this free body with angular velocity having component in z direction, and that is why Cz will still be 0. So in this case also we are dealing with only one unknown scalar, that is F, and that F is a force along perpendicular direction of the frictionless rod or the slot that has been shown on the right hand side of this figure. So this was my last slide on supports and various kinds of support and reaction force systems that develop, that are generated by these supports. Okay. I hope everything is clear to the students who are sitting there. And paying attention to their notes, I hope. All right, I move to a new topic. This new topic is handling Euler's second axiom. How do we handle Euler's second axiom? I have said earlier that as far as dynamics problems are concerned, Euler's axioms will be used. Euler's axioms will help us predict the motion of an RB subject to a given force system. Two axioms exist, first and second axiom. First axiom is to remind you, Euler's first axiom tells us that the net force acting on an RB is mass times acceleration of its center of mass with respect to an inertial frame. Inertial frame. Right? Where there is the external force system, eventually we can express as the simple resultant, or as a resultant force system at any point B of our choice, as we have seen. Now, as far as the first axiom is concerned, it is easy to handle. F will be a known vector, mass is known, ACI is a vector that can be directly found using this relationship. F divided by M will give you ACI. And then if you want, you can time integrate to get velocity, and time integrate velocity to get the displacement of center of mass. I would say that it is algebra is easy to handle, straightforward to handle. When the need arises, we can do this. We can deal with this equation, find ACI. However, when you go to the Euler's second axiom, even though we may not realize it right now, just looking at this equation, I'm telling you it is not straightforward to deal with this equation. Why it is not straightforward to deal with this equation is, the reason is handling this term. What is this term? Rate of change of angular momentum of the RV about point O with respect to I. Recall that I have earlier given you the definition of the angular momentum of a body about point A and with respect to a frame. The frame here in Euler's second axiom is an inertial frame I, and the point about which the angular momentum is to be found has to be a point fixed in I. Now HOI is an integral. I have written this expression here. RPO cross VPO with respect to I dm. This integral makes it difficult to handle the algebra of this. First, it is an integral even at time t. I mean, this is the HOI at time t. You will have to integrate. And then that is not all. Please realize that in Euler's second axiom, you have to deal with the time derivative of that integral. Okay? Two complications. Integral at time t, and then time derivative of that integral. That's why I say it is not straightforward to handle. Thus, we need to learn a few things about the left-hand side of this equation before we can comfortably solve dynamics problems. We need to learn a few things about how to handle the algebra of the left-hand side. Okay. There are specifically three things we need to learn. Three things to learn. Whatever is the first thing, I will talk about that immediately after this slide. The second thing that needs to be learned, I will talk about it in continuation, either today or on Monday. The third thing, I will talk about maybe like 2 weeks later. Because to learn about that item number 3, we need again many new concepts in between. For the time being, I want to pose this big picture that there are 3 things to be learned before we come back and solve this equation. Okay? Now let's go to these first 2 things now. So I will first tell you what is the thing to be learned, and then I will explain the procedure. What should be followed. Now, before I leave this slide, I also want to highlight that right hand side of this equation is the net moment due to all forces acting on the body. This is again a quantity which I do not consider challenging, in the sense that if you know FR, you know CRB, what is shown on the slide on the right hand side, it is straightforward to find MO. It is only the left hand side that will create trouble, will be challenging. Okay. We take a break now. We'll meet at 5:05. We have lost some time today, so I'll give you a 5 minutes break.